Hello, here we are. It's April 6th, 2015, and this is part 3 of the Jolida amplifier repairs. I saw a video on YouTube, and they were talking about having a scope connected to both the DC output of a bridge rectifier and the input. And it was creating some anomalies on the scope. So this is a Fluke 190 oscilloscope. It's fully independent, and it's got floating grounds on it. So it should not have been in effect. So we just wanted to verify that by disconnecting the DC input to the scope, which is the output of the bridge, and verify that this is not a source of our problem. So here we go. Let's get down. We got a variac over here. Variac is controlling the power input to the amplifier, and we're able to crank it up and observe the oscilloscope. And we can see, as we're right from the start, this signal is clipped, and as we turn it up, it just continues. Our configuration right now is we're running series capacitors on the output. This is the Jolida's actual configuration, where they take two caps. They connect them in series and use a voltage divider to ensure that each cap has the same voltage across it. But we can see that having one channel or DC output of the bridge disconnected from the scope has no effect on the performance here. For whatever reason, this is still clipping, and that was the display on the oscilloscope. And once again, there's the breadboard. You can see two resistors on there with the 4 diodes, and then there's our two caps that are in series. So that's the oscilloscope is not the source of this. There's something going on when we have capacitors connected to the output. Maybe what we'll do next is we'll disconnect these caps and re-verify what the signal looks like. It should be a clean signal. We'll have both channels connected up. So stand by one, and we'll get that connection made. Okay, we're back. We got the correct configuration. The capacitors have been removed from the Jolida bridge output. That's on this breadboard down here. The caps have been disconnected. So we'll turn this thing up, and we'll take a look at what the signal looks like as we increase the variac voltage. Okay, we can see that this thing is pretty smooth. There's both channels coming up, and that anomaly is not present. There's 780 volts off the power transformer, off the secondary, which is feeding into the bridge, and then there's our peak to peak off the bridge, or actually peak voltage off the bridge, which is 390 volts. So that looks pretty good. Take it back down. There you have it. Alright, clean signal. Cap's disconnected. Cap's not in the circuit. And you see the DC here as we increase this up. 1 meter is showing milliamps, and the other meter is showing us the DC output. 230. As I reach the max, got about 250 and 600. Okay, there's our load down there, some 100-watt light bulbs. But there you have it, on 260 and 669. I don't know what the exact input voltage is, but the output voltage right now is 790 peak to peak. I don't have the meter on the input to the amp, so we'll just leave it there. Perhaps try another configuration on the breadboard. Okay, we're back. We got another configuration here. We're running with the Schottky diodes, and we went to the stock Jolida configuration of 2 capacitors and a voltage divider. Alright, so these are, I believe the schematic for Jolida shows 68 k-ohm resistors for the voltage divider, which is what this is. And then we've got the 2 caps over here, 470 microfarad 400 volt caps. Got the voltage divider, the Schottky diodes on the breadboard, and then we've got our current and voltage, DC voltage meters over here. Got our load, some 3 100-watt light bulbs. We also set up a secondary load that we can try maybe for the next step of 3 40-watt to see if dropping the load will have an effect on the clipping of the transformer clipping. So let's get started here. There's the amp. There's our input voltage, which is 625 millivolts. I'm going to turn that up. And here's our oscilloscope. So here we go. Alright, 30 volts. And just so you can see it, we're clipping right from the get-go again. We're at 47, 50 volts. About 70 volts now. Input into the amp. Climbing through 90. About 115. And that's about wall voltage right there of 120. That's input into the amp. For an output, we've got 690 peak to peak on the AC, and an 18 volt ripple. This is with the series capacitors and the voltage divider, which is Jolida's stock setup. Alright, we timed out on the scope there. Let's take a look and see what we got over here. We got 328 volt DC, and we're pulling 789 milliamps of current, and the light bulbs are pretty bright. So maybe we'll drop the current draw to smaller light bulbs, and we'll see what happens. So 680 with an 18 ripple, maybe with the smaller. There's the input into the amp. So standby 1, we'll change over those light bulbs and we'll see what happens. Okay, we're back once again. We changed the load to a smaller load. Down here we've gone to 3 of these small 7-watt bulbs, so this should be a 21-watt load. And we're going to take a look at see what effect it has on the voltage and current of the DC output of the bridge. We're still running 2 470 microfarad capacitors in series with a voltage divider of I think there's 68,000 ohms on that voltage divider each. Well, here we are. We haven't touched the variac, so we're just going to switch it on, see what happens. Okay, we've got 121, 122 volts input into the amplifier, and that's going into the transformer, the power transformer. And look at this, we've got 840 volts peak to peak on the secondary. So obviously dropping that load with a 2.1 volt or 2.2 volt ripple. Obviously if I didn't have any draw on the secondary of the transformer, it would be doing pretty good. Once again, this is with a 21 watt load. We got 413 volts DC on the output, and the 21 watts is drawing 66 milliamps of current. And there they are, 3 light bulbs up. This is what we'd like to see with the amplifier producing music at about 40 watts output. We'd probably be able to get almost 60 watts of output from this amplifier if we could get the plate circuit to see this kind of voltage, which is what they state that this amplifier is capable of. Maximum 60 watts output. Might have a high distortion, but that's what they say. That's what the specification on the amp is. Alright, so we're going to try no load. Let's disconnect the light bulbs. See if we can do that without killing ourselves. Let's switch the amp off. Alright, voltage is down to 0. We'll just disconnect this current meter, which should open up that light bulb circuit. And let's see what happens here. I'll switch the amp back on. 122 input into the amp. Alright, there's the secondary with no load, 870 volts peak to peak with a ripple of 0.2 DC. Let's increase that a little bit. There you can see the ripple. That's the bridge rectifier with no load on it. So it's a 0.22 volt DC ripple, 870 volts peak to peak on the output of the transformer, the power transformer in this amplifier. Let me take that down a step. And once again, there's the amp. There's a bridge circuit. But right now, the only actual load on it are is a voltage divider. Those 68,000 ohm resistors are providing a drain or a load to these Schottky diodes. So that's what we're looking at there. So that's 68,000 ohm. I didn't calculate that out. But we got 426 volt DC output, and obviously 0 current because we're not in microamps. I don't think we'd actually be measuring the current of the divider at that where that meter is placed. Okay, light bulbs are off. But this is what we'd like to see with this amplifier working, which actually we're probably around a 326 volt DC when the amplifier is turned on and we're producing music. So that's what it is. Let's see what we can do with this, and we'll be back. Okay, we're back. We made another configuration change. Another breadboard here, and on this breadboard these are the original model diodes that came in the amplifier. They're 1N5408, and we set up the voltage divider. I think these are 62,000 ohm resistors in series, and then we've got the two 470s tied across that voltage divider so that the voltage is equal on each cap. Alright, let's get this thing cranked up and we'll see what happens here. Right now we've got no AC input, so we'll just switch. We haven't touched the variac control. It's been the same all throughout, and right now we've got 850, 840 volt peak to peak. You can see a slight clip on it. We've got 2.2 volt ripple. This is with a 21 watt load. We're running those small light bulbs, the itty bitty ones, 7 watts so we should have 21 watt. We're producing 417 volt at the output, and we're drawing 67 milliamps. So that's what that looks like, and that's the single right there. So obviously as we decrease the load, the clip gets much smaller. Too bad that the amplifier didn't run with this kind of load on it, but when you're trying to draw the recommended or rated output of the amp, the clipping is much greater, and we got a much greater loss on that secondary, so that equals out to a greater loss at the tube plate circuit. So let me get another change in here, and I'll be back. Okay, we're back again. We went to the big light bulbs. We got 300 watts to draw right now. So again, the variac hasn't been touched. All we did has been switching it on and off. We've got an 18 volt peak to peak ripple and 690 volt peak to peak with the clip. This is what the amplifier is actually seeing. There's our input into the amp, 120 volts. This is what the amp actually sees as a load when we're probably producing about maybe 30 to 40 watts of output. They've got 327, 328 volts DC going into the 3 100 watt light bulbs, and we're drawing 790 milliamps of current. So this is what the amp is actually seeing, and this is what we're trying to figure out how we can increase this. Once again, these are the original model type diodes. They're new diodes, but they're the original model diodes that were used in the amp, and these caps are the original microfarad capacitance that the 470s. There's two of them in series with a voltage divider. So this is what the single looks like, and we're trying to improve on this. It'd be great to get that 680 up to 780. Another 100 volts would be great. So we're going to be working on that. Okay, we're back again. We went a whole new direction here. We disconnected the transformer of the secondary, and we have come directly out of the variac. We'll pull right out of the variac to these two wires, and we've got our AC meter hooked up to that, and then we also we go directly from the output there of the variac right into the bridge. Everything on the bridge is identical. Haven't changed anything there. Still got the caps in series, the voltage divider. We've got the 3 100-watt light bulbs is the load, and meters and everything else is. So the only thing we've changed is we've taken the power transformer of the amplifier out of the circuit. So now we want to see what happens here. So let's take a look. Alright, we're coming up. This is the Variac output. Pretty smooth, huh? Alright, we've got 17 volt ripple. Looks like 400 volts peak to peak. Output from the Variac. That equates to 144 volts RMS output from the Variac. And the single is not clipped. These capacitors, everything else is identical. So it's starting to look like the transformer on the Jolida is just running out of gas when we're trying to run this thing. Once again, we're running the stock diodes here, the 1N5408s. The caps, this is how Jolida sets up their caps, are in series. We're drawing 584, 85 milliamps, and the output is 188 DC volts, and those are going into the light bulbs. Not as bright, obviously. It's a 300 watt load. There's the current, and there's the breadboard, and there's the signal showing that the primary is not clipped. So it doesn't have anything to do with, it's starting to look like it doesn't have anything to do with the capacitors or the diodes. It's starting to look like the transformer is just running out of gas. So that's not good. We'll start looking at that, and we'll go on from there. Okay, here we are once more. What we did is we pulled off the top to the transformer, and I don't know if you could see it down there, but it says 300 volts, 300 milliamps off that high voltage line. So we set up a little test for it, and basically we got is we're measuring the AC voltage and the AC current. Once again, we're using this. These are, I think, 60 watt bulbs, 3 of them, all hooked up in series to take the voltage. Let's see what happens when we turn it on. There you have it. That's 300 volts AC, 305, and the current draw is 300 milliamps. No problem. So I guess we're going to have to go back to the drawing board on this and try and figure out what's going on, why this thing is dipping on its voltage. But according to the nameplate on the transformer, this is what it's supposed to be doing, and that's exactly what it's doing. Alright, we'll be back. Okay, we're trying it one more time. Once again, that's the transformer. It looked pretty good when we opened things up. And it says 300 milliamps at 300 volts. That red and black wire up there on the top left. So that's what the transformer says. Let's turn this thing on. There you have it. We're doing 298 volts, 450 milliamps. We upped our light bulbs to 60s. They were 40s before, so we got 60s in there now. So transformer's performing pretty good, at least according to the data plate that's on it. So like I said, it appears it's going to be back to the drawing board on this thing at why this is not able to produce 400 volts on the plate circuit for the output tubes. Alright, we'll be back.